Welcome to this online video tutorial. My name is Maria Murcia and I work under the supervision of Professor Amadeo Rodríguez Fernández Alba at the EURL-FV. This video tutorial will discuss the main features of different splitless liners employed in gas chromatography and to give an overview of which ones are more suitable for each specific use. Liners are glass devices which are placed in the injector of a gas chromatograph, and they provide a space to evaporate the liquid samples before the chromatographic separation. There are a lot of geometries and configurations, and also various companies providing unique features to the liners. One of the main differences among the manufacturing companies is the glass deactivation. Liners possess active sites where certain matrix components or even the analytes can be adsorbed, and each company performs a specific deactivation process to eliminate these active sites. However, all these characteristics might be confusing, and one might have difficulties in choosing an appropriate liner. In terms of geometry, liners can be straight, which is with uniform internal diameter, or they can have a single or double taper. Tapers are funnel shapes which could help minimize the interactions of the sample with the inlet and focus the analytes to the column. A taper on top of the liner could also help reduce the loss of analytes during the evaporation. There are also liners with a special geometry, which are developed by specific companies. There is also the possibility to include glass wool or frit inside the liner as a way to provide a solid support for the sample and facilitate the evaporation, and also to prevent the non-volatile sample components from reaching the column. However, some labile analytes might be lost through interaction with this component, and the packing of the wool could affect the reproducibility. Another feature of liners is their internal diameter. A reduced internal diameter could help transfer the sample to the column in a narrow band due to the increased flow and gas velocity. However, the maximum capacity of these liners should carefully be considered because if the volume after the sample evaporation is higher than the maximum capacity of the liner, part of the sample will flow over the top of the liner. This will result in a loss of sensitivity and reproducibility, and probably in the inlet contamination. We will now compare how these configurations affect the liner performance. We selected 9 different liners from 3 companies so as to maximize the information obtained from each design and manufacturer. The first 3 liners contained the best-selling splitless configuration, which is single taper, glass wool, and 4 mm of internal diameter. Each one was provided by a different company, so any differences in the performance of these 3 liners is probably due to the preparation process and concretely the deactivation approach. Liner number 4 had the same geometry, but its internal diameter was 2 mm instead of 4. Liner number 5 had a special geometry consisting of a double taper and a spiral in the lower half. This geometry was developed by the manufacturing company, and it was supposed to enhance the sample evaporation. Liner number 6 was similar to the 1, 2, and 3, but in this case without the glass wool. In liner number 7, the glass wool was replaced by gas frit, so the packing was slightly different. Lastly, in liners number 8 and 9, there was a glass frit or glass wool in an intermediate position instead of the bottom. As regards the instrumental parameters, the analyses were performed on an Intuvo 9000 coupled to a 7410 triple quad. The inlet parameters are the most significant for this study, and specifically the total volume of sample after the evaporation. It was calculated to be 140 microliters, which is much lower than the reported maximum capacity of all liners. Regarding the experimental design, there were 9 consecutive days of injections, each one with a different liner. The injection sequence was always the same, and it was separated in 2 parts. For the assessment of the signal intensity that could be achieved by each liner, we randomly selected one of the first 3 liners as the reference. Each day, a new liner number 1 was used to perform 3 reference injections. The vials contained a mixture of 188 pesticides in tomato matrix, with different concentrations from 5 to 200 ppb. This means that the sequence started each day in the same form. First, 3 injections of the reference liner at 3 different concentrations, followed by other 3 injections using the liner that was being evaluated. Then, the areas provided by both liners were compared for each concentration level, and a unique value was calculated for each compound as the average of the 3 concentration levels. So, a value above 100% means that the liner being evaluated provided a higher sensitivity than the reference liner, whereas a value below 100% means that the reference liner performed better. In these graphs, each ball represents a compound. There were no significant differences in the sensitivity when using liners number 1, 2, and 3, so it seems that the activation process does not affect this parameter. The same happened with the special geometry in liner number 5 and the absence of packing in liner number 6. In both cases, most results were similar to the reference liner. But a different scenario was observed with liners number 4 and 7. In the first case, the reduced internal diameter resulted in a significant increase in the sensitivity. Conversely, the use of a glass frit instead of a glass wool in liner number 7 resulted in a loss of sensitivity for the vast majority of compounds. Let's have a closer look at this. These are some random compounds from the GC method. When we compare the sensitivity of the reference liner with itself, that is, liner number 1 with liner number 1, we obtain values very close to 100% as expected. This is the variation in the areas obtained with liner number 4 with a reduced internal diameter. In some cases, the signal was up to 50% more intense. However, with the use of liner number 7, the areas were lower than those of the reference liner. Here you can also see that some compounds were more affected by these effects than others. For instance, chlorotoluene undergoes a very strong increase in the sensitivity with liner number 4, but it is not affected by the use of liner number 7. For the durability and peak shapes, we prepared daily 6 injection vials with 3 replicates of each one. The matrices selected were tomato and orange at 3 concentration levels. First, 4 injections were performed on each concentration level in tomato, and these vials were then discarded. Afterwards, the same was made with the 3 concentration levels in orange matrix. Then, the same again with tomato, and so on until all vials had been injected 4 times each. Therefore, there were a total of 72 injections performed with each liner. According to this experimental design, the durability was assessed individually for each pesticide by comparison of the areas provided by the first and last injection in each matrix and each concentration level. An area in the range of 80 to 100% indicates that the liner is still suitable for further analysis of that compound. Conversely, values lower than 70% of the first injection indicate that the liner is not in good condition anymore. The intermediate values correspond to compounds whose area was starting to decrease. These graphs show the number of compounds that fall in each category. Blue bars represent tomato and orange bars, orange matrix. Remember that the only difference among liners 1, 2, and 3 was the manufacturing company. The performance of liners 1 and 3 was very similar, whereas liners number 2 provided a shorter durability in tomato matrix. The deactivation procedure employed by one of the companies might be related to the loss of sensitivity of certain compounds. Similar trends were observed for liners 4 and 7, number 4 having smaller internal diameter and number 7 with glass frit instead of glass wool. Interestingly, in liner number 6, the absence of packing resulted in a better performance for tomato matrix, providing very good results in terms of durability. Lastly, the special geometry in liner number 5 might have influenced its shorter durability in both matrices. Now we'll talk about the peak shapes. In this case, the evaluation was based on a visual evaluation of the peak shapes of all compounds for both matrices and all liners. We could see that the liner configuration did not affect the peak shapes of any compound, with just one exception. First, this is an example of how the peak shapes were always the same, regardless of the liner. These are the signals of bixafen at 50 ppb in tomato matrix, virtually the same peak shapes for all cases. This happens with 187 compounds. And this was the only exception, biphenyl in tomato matrix. In this case, the narrowest peak was obtained with single table liners, that is, numbers 1, 2, 3, and 6, whereas the remaining geometries resulted in poorer shapes. However, it is remarkable that this effect was not observed in orange matrix with any of the liners assessed. The presence of more matrix components in this sample might have hindered the influence of the liner on the peak shape of this compound. Lastly, I avoided talking about liners number 8 and 9 in all the previous slides, because these two liners were the only ones with a packing in mid position, and the results were surprisingly different from the remaining liners. The maximum capacity was supposed to be higher than our sample volume after the evaporation, and also the manufacturing companies state that these liners are suitable for splitless injections, but the results we obtained did not show the same. These are the signals of diazinon and the tofenprox in tomato at 50 ppb. You can see that liner number 9 resulted in the complete loss of the peak, and that with liner number 8 the signal is much wider. But also with liner number 8 there was a dramatic loss of sensitivity. These chromatographs are not scaled. If we do so, it is obvious that the signals provided by any of these two liners were not suitable for sample analysis. In the majority of the 188 compounds, the areas obtained with liner number 8 were between 3 and 15% compared to liner number 1. In other cases, the signals provided by liner number 8 were pretty wide, as in the case of dichloran and picolinafen. And again, the sensitivity decreased enormously. In most cases, liner number 9 did not provide any kind of chromatographic signal. Thank you for your attention. We, from the EURL-FV, hope this tutorial was useful for you. Now you will see some self-assessment questions to revise the topics covered in this video.